So as we've talked about previously, a torque causes an angular acceleration. This is the rotational equivalent of Newton's second law for motion along a line, that a force causes an acceleration. Now, to see where this connection between torque and acceleration comes from, we're going to start by examining a single particle subject to a torque. This picture here shows a particle of some mass attached to a lightweight, rigid rod of some length that constrains that particle to move in a circle. The particle is subject then to two forces. It's moving in a circle, so there must be a force directed toward the center of that circle. Here it would be a tension from the rod. Now, what we need to understand about that tension is that it's the force that's responsible for changing the direction of the particle's velocity. The acceleration associated with that change in the particle's velocity is the centripetal acceleration, and that's directed toward the center of the circle. But this particle is also subjected to a force that changes the speed of the particle. This force causes a tangential acceleration. So it's this tangential force that causes this tangential acceleration in a direction tangent to the arc. If we apply Newton's second law to that direction tangent to the circle, then that tangential acceleration is equal to that tangential force over the mass. Now, the tangential and angular accelerations are related by AT equals alpha r. So that if we equate these two equations, we can rewrite them as alpha equals F over mr. So now we can connect this angular acceleration to the torque because the force, which is perpendicular to the radial line, exerts a torque. So the torque, of course, is Rf. So with this relation between force and torque, we can rewrite this as alpha equals torque over mr squared. This gives us a relationship between the torque on a single particle and its angular acceleration. Now all we have to do is to expand this idea from a single particle to an extended object. Okay, so this picture here shows a rigid body that undergoes a rotation about a fixed and unmoving axis. So according to our rigid body model, we can think of this object as consisting of particles with masses m1, m2, and m3. Each of these masses then are at some fixed distance from the axis. Now suppose the forces F1, F2, and F3 act on these particles. And these forces exert torques around that rotation axis so that the object will undergo an angular acceleration. So because all the particles that make up the object rotate together, each particle has this same angular rotation. So if we rearrange this equation, we can rewrite each torque respectively as torque equals the mass times the square of the radius from the axis of rotation times the angular acceleration. And we can do this for each one of these torques, which will give us this net torque expression, right? So what we have to make use of here, though, is that this angular acceleration for each of these particles is the same. So we can factor out that angular acceleration so that we get that net torque is equal to that angular acceleration times the sum of, this is a sigma, so it's sum of the individual masses times the square of the individual distances from the axis of rotation. By doing this, we're making use of the fact that every particle in a rotating rigid body has the same angular acceleration. Now, this quantity, this sum of mr squared, is the proportionality constant between angular acceleration and net torque, and we call it the object's moment of inertia. So moment of inertia is this proportionality constant between angular acceleration and net torque. We symbolize a moment of inertia with a capital letter I. It's a quantity that expresses a body's tendency to resist angular acceleration It's the sum of the products of the mass of each particle in the body with the square of the distance from the axis of rotation. Our equation for moment of inertia, then, is the sum of the individual masses times the square of their individual distances from the axis of rotation. Now then, from this equation, we can see that the units of moment of inertia are going to be kilogram meters squared. And we have to realize then that an object's moment of inertia, like torque, depends on the axis of rotation. Once that axis is specified, then allowing the different values of r to be determined, the moment of inertia around that axis can be calculated from this equation. Now, realizing that, and when we look at this equation here, we can see that if we substitute in the moment of inertia, it puts this final piece of the puzzle into place, giving us the fundamental equation for rigid body dynamics, which is angular acceleration is equal to the net torque divided by the moment of inertia. This tells us that an object that experiences a net torque around the axis of rotation undergoes an angular acceleration. The I here is the moment of inertia of the object about that axis of rotation. And this here will be the equation that you'll see on your equation sheet. So now, to get a better understanding then of moment of inertia, we have to realize that moment of inertia is the rotational equivalent of mass. Okay, so what this means is rotational inertia plays the same role in this equation as mass does in this equation. Now remember, objects with larger mass have larger inertia, meaning they're harder to accelerate. So an object with a larger moment of inertia is going to be harder to get rotating. It takes more torque to spin up an object with a larger moment of inertia than an object with a smaller moment of inertia. So the fact that moment of inertia holds the word inertia reminds us of this. But then we also might think, why does the moment of inertia then depend on the distances from the rotation axis? Well, think about trying to start a merry-go-round from rest, as shown here. By pushing on the rim of the merry-go-round, you exert a torque on it, and its angular velocity begins to increase. So if your friends sit at the rim of the merry-go-round, their distances from the axis of rotation are large. The moment of inertia then is large, according to this equation, and it's going to be difficult to get the merry-go-round going. However, if your friends sit near the axis of rotation, then their distance is smaller and the moment of inertia is smaller. You're going to find it's much easier to get the merry-go-round going. So an object's moment of inertia depends not only on the object's mass, but also on how that mass is distributed around that rotation axis. It's because of moment of inertia that bicycle racers will use the largest possible tires that they can. The larger the moment of inertia, remember, the more effort it's going to take and the slower their acceleration will be when they're trying to accelerate. For this reason, they'll use light tires, and they put those tires on wheels that have been designed to keep the mass as close as possible to the center without sacrificing the necessary strength and rigidity. So then, to summarize rotational dynamics and linear dynamics, we have this lovely little table here where we've got linear motion and rotational motion. So the counterpart to position in linear motion is angular position in rotational motion. Velocity is angular velocity. The comparison between acceleration is angular acceleration in rotational motion. For linear motion, we talk about force. In rotational motion, we talk about torque. For linear motion, we talk about mass. For rotational motion, we talk about moment of inertia. We can talk about angular acceleration with rotational motion, and that's linear acceleration with linear motion. And of course, the big one, Newton's second law, is F equals ma for linear motion, and it's moment of inertia times angular acceleration for rotational motion. What I really like about this table too is it shows their equivalents for each of the motion equations as well in the rotational motion. And also we've got kinetic energy here is 1/2 mv squared. For linear motion, it's 1/2 moment of inertia times angular velocity squared for rotational inertia, and we've got power here as well. You should really take some time here to really take a look at this and make sure you understand the analogies, the connections between linear motion and rotational motion. Now, Newton's second law for rotational motion is pretty easy to write, but we can't make use of it without knowing an object's moment of inertia. Unlike mass, we can't measure moment of inertia by putting an object on a scale. Although we can guess that the center of gravity of a symmetrical object is at the physical center of the object, we cannot guess that the moment of inertia of even a simple object. So for an object consisting of maybe only a few point particles connected by some massless rods, we could use our moment of inertia equation to directly calculate it. But such an object is pretty unrealistic. All real objects are made up of solid material that is itself composed of countless atoms. To calculate the moment of inertia of even a simple object requires integral calculus and is beyond the scope of what we're doing in this course. So a short list then of common moments of inertia is given here. Now in each of these, the capital M will be the total mass of an extended object. Now you're not likely going to need to have these locked in your brain, memorized, right? But you should be aware that they exist and be able to work with them in our practice work. Now your textbook goes into a great section looking at several examples of rotational dynamics for rigid bodies that rotate around a fixed axis. And what this does when we rotate things around a fixed axis, it avoids complications that could arise from an object undergoing a combination of rotational and translational motion, like the flying hammer or something. So we have here a problem-solving strategy for rotational dynamics, and it's really similar to a problem-solving strategy for linear dynamics. You should really take some time to take a look at the examples given in the textbook, as the scope of the video here is really on the conceptual nature of this material. But essentially, when you go to solve problems of these, right, you want to first model that object as a simple shape. You want to draw pictures and define coordinates and symbols and list known information. You want to identify the axis around which that object rotates, identify the forces, determine their distance from the axis. So we're looking again at forces involved here. We can throw Newton's laws, of course, into this. We want to be able to then calculate torques caused by those forces and find the signs of the torques. So we're utilizing information about torques that we've got in the first lesson. And then use the mathematical representation based on Newton's second law for rotational motion. And then find that moment of inertia by direct calculation, or from that list of common shapes in the previous slide, and then use rotational kinematics to find angular positions and velocities. But really, what we want to do here is be able to take a look at the concepts of this stuff here in the video, and we'll be looking at problem-solving quantitative examples in class. Now, there are a lot of important applications of rotational dynamics that involve objects that are attached to ropes that pass over pulleys. So this figure here shows a rope passing over a pulley connected to an object in linear motion. Now, in situations like this, if this pulley turns without the rope slipping on it, then the rope's speed must exactly match the speed of the rim of the pulley. Now, the speed of the rim of the pulley is omega r, where omega, of course, is the angular velocity here, and the r is the distance from the axis of rotation. Now, because the rope is over the pulley and the rope is not slipping, if the pulley has an angular acceleration, then the rope's acceleration must match the tangential acceleration of the rim of the pulley, which would be the tangential acceleration would be alpha r. Now, because there's an object attached to the end of the rope, then that object that's attached to the end of the rope must have the same speed and acceleration as the rope itself. Consequently, the object must obey these constraints, where the velocity of the object then is equal to the omega r of the pulley. And the acceleration of the object is equal to the alpha r also of the pulley. So these constraints are similar to the acceleration constraints when we talked about Newton's laws, when we put linear motion together and have multiple objects attached by strings and ropes and pulleys and whatnot. So these constraints are very similar to that and need to be treated in the same type of way. And you have to remember too that these constraints, just like with Newton's laws, are given as magnitudes, and we have to look at specific problems. Remember, like Atwood's machine problems, that would require us to specify signs that depend on the direction of motion. So we'd also have to look at the direction of these constraints as well. So make sure you take some time to look at the examples presented in the text, and we'll look at some in class as well, and of course have some practice opportunities. We'll see you then.